So today you're gonna learn to measure distances using sound that's imperceptible to the human ear. Sounds cool? That's cause it is. Let's get right into it. This is the HC SR04, the most common model of ultrasonic sensor which comes in most starter kits.
An ultra super what?
An ultrasonic sensor is a module that emits ultrasound, i.e. sound with a frequency so high that humans can't hear it, and can then detect when that emitted sound arrives after bouncing off a surface. Knowing the speed of sound, 343 meters per second, if we measure the time it takes to come back, we can tell exactly how far away that surface is, effectively creating an invisible remote meter. And we can use this to do so much more. After all, they're used everywhere from your car to every starter robot's face. I mean, my conscience would not let me punch that. Something really interesting is how this module proves that in electronics, stuff often goes both ways. If you spin a motor, you get electricity, if you power a solar panel, you get light, and in this case, if you vibrate a piezoelectric speaker, which is what's inside of these cylinders, you get electricity. In fact, these two are exactly the same, just that one is electrified to produce the sound, and the other one receives it, producing an electrical signal we can measure. Okay, so how do we wire it? Well, it's really easy. There's only 4 pins and they're labeled. As always, there's VCC and GND, connected to 5 volts and, well, GND. And then there's the middle pins, trig and echo, which you can wire to any pins. Trig will receive the signal to emit the ultrasound, and echo will send the signal back to the Arduino when it arrives. And now, with the wiring done, we can get to the code. The first thing we'll do is, as always, declare our variables. And we'll have 2 floats, so decimal numbers. One will be the time, so the time it'll take for the wave to come back, and the other one will be the distance, which is what we want to get. And now in our void setup, as we're going to be reading the distances on our serial monitor, we'll just initialize that, and we'll also set our pin modes. I chose pin 4 for the trig pin and pin 5 for the echo pin, so I'll do pin mode for output, because remember the trig pin will send the signal from the Arduino to the sensor to produce the wave, and pin mode 5 input, because the echo pin receives the signal from the sensor when the wave arrives. And now, in our void loop, we're actually going to learn a few really useful new functions here, but the first thing we need to do is generate the wave we're going to send. And to do that, we first of all need to set our trig pin to low. So let's do that, and then we'll wait. But here, as we're working with extremely quick stuff, I mean literally the speed of sound, we won't use normal delays with milliseconds. Instead, we'll use delay microseconds. 1 microsecond is 1,000th of a millisecond, and we'll wait for 2 of them. So this will wait for 2 millionths of a second, which is insanely precise. And then we'll send our actual pulse. So let's do digital write our trig pin high for 10 microseconds. Alright, so we need to send a 10 microsecond pulse. And then of course, let's set it back to low. Alright, but wait a minute. Why do we write a low here if we're already setting it back to low here? Well, for 2 reasons. First of all, when you first plug in your Arduino, you don't actually know which state your pins are in, so it's always a good idea to set them manually to whatever state you want them to start at. And second, because as you can see here, we don't have a delay at the end of this. And you might actually not have a delay because you might need, really fast, continuous measurements. And if we remove this, we would just have, this pin 4 to high for 10 microseconds, and then we'd set it to low, but immediately again to high. And we're not waiting, so it's literally spending exactly 0 time at low. So the sensor might not actually detect that it's ever gone low, and it might never send a 10 microsecond pulse. So yeah, that's why we have that there, and this is how you generate our wave. And now, we'll use our second function, pulsing, to get our time. So we'll do time equals pulsing our echo pin high. And what does this do? Well, pulsing, what it does is it assigns to this variable however long it waited for the pin we give it to get to the state that we give it. So basically, this will be waiting for pin 5 to go high, and it will tell us, it will store in our time variable how long it waited for that to happen. All right. So yeah, this is literally how we wait for the wave to arrive and get how long that was. However, we know that the speed of sound is 343 meters per second, but this gives us the time in microseconds. So what we'll just do is turn it into seconds by just dividing it by 1,000,000. And remember, let's add a .0 here so it doesn't treat it as an integer division. All right? And now we have our time. But how do we get the distance? Well, as I said, we know that the speed of sound is 343 meters per second. And so we just need to multiply our seconds, so time, times the meters per second, so 343. And this will just give us the distance our wave traveled. However, remember that this keeps in mind the time it took to go and come back, meaning it's actually giving us double the distance that we actually want to measure. So we literally just do divided by 2 to get the actual distance of, one way. And well, this will give you the distance in meters. And usually you work in some kind of room or something like that, so you might want them in centimeters instead. And to do that, really easy, we just multiply by 100. I mean, you can just omit this if you want them in meters, but this is more convenient in my opinion. And well, that's our distance. So let's just print it now. So serial.print distance, and I'll just do serial.print on centimeters. All right. We could add a delay at the end here, but it's not really necessary, so I won't do that. And we can now test this. So let's now open our serial monitor, and we should have our distances being printed. So I'm holding it, pointing at a wall right now, and if I get it closer, the distance goes down. If I get it further away, the distance goes up. And if I cover it up close, yeah, a really short distance. So yeah, we've made a completely invisible remote meter. How cool is that? But you know what's even cooler? With everything you've learned so far, you can now make your own DIY alarm system. To do this, we'll add a buzzer, preferably an active one, to our circuit and wire it just like we learned, negative to ground and positive to any pin. For the code, we can actually keep most of what we already have. Well, we don't really need to print it anymore, it doesn't really matter. And we'll just add our buzzer pin to our pin modes. So I chose pin 6, so that'll be an output. And then we'll have an if statement to activate our alarm. So we'll say if our distance is lower than 100 centimeters, so 1 meter, then we will activate, so this is alright, 6 high. We will activate our buzzer for how long? 60 seconds. No mercy on those eardrums. And then turn it off again. Alright, so yeah, if our sensor detects that the distance is less than 100 meters because someone has passed in front of it, then it will start making an unbearable sound for 60 seconds. So yeah, let's try this out. Alright guys, so I'm gonna place my trap on the front door. So place it here, plug it into this. Ideally, I'd have a battery to make this more portable, but I'm on vacation and I forgot to bring my battery, so yeah, I'll just have to stick to this plug, but it should work. So in theory, When this door opens, the distance should fall below 1 meter, and it should sound the alarm. Okay, now let's wait.
I am a very naughty criminal, and I am going to break into this house. Oh no! It's a nerd's house! Run!
That was fun. But you know what's also fun? Designing your own custom PCBs and having them printed in real life. You can make any kind of circuit you can imagine, and it's the gold standard for actual electronics products. I mean, it's the difference between this and this. Now, you'd think such advanced, precise manufacturing would set you back a ton of money, but see this? It's a custom PCB that does basically everything an Arduino can do. Well, it costs $3. Except that thanks to today's sponsor, NextPCB, you can get it for a single cent. Because for your first order of a Rev 0 PCBA, which is a board with all the parts already soldered, electrically tested, and ready to use, and if you use the link in the description, you'll also get a free $10 coupon for any further orders, and at no additional cost, you'll be supporting my projects every time you order a PCB. So thanks to NextPCB for sponsoring this video. The channel is going through a rough time and it's gone from 79,000 to 77,000 subscribers, so it would really help if you subscribe if you haven't yet, turn that bell on, and leave a like if you enjoyed. Thanks for watching, and I'll see you in the next one.